Okay, the law of conservation of momentum. And in this video, we're going to focus on linear momentum, meaning that it's momentum just in a straight line. Okay. So, what is the law of conservation of momentum? Well, basically, it's just like the law of conservation of energy. So, the total momentum before any event has to be equal to the total momentum after the event, right? So however many different objects you have, you just add up the individual momentums of each one and you set it equal to the momentum of each object after the collision, right? Plus m2 v2 final plus however many, okay? So we're just adding momentum before and setting it equal to momentum after a collision or after an interaction. Okay, so let's take a look at an example. So a basic cannon. So we have a cannon. Let's say the cannon has a mass of 800 kilograms. And it fires a 10 kilogram ball at 100 meters per second. Okay, so this ball has some momentum, so it gets fired this way. The cannon, after the explosion that fires the cannonball, will roll backwards, right? And that's due to the law of conservation of momentum. The total momentum initially is 0. So the total momentum here also has to be 0, right? So again, we're looking at the initial momentum and comparing it to the final momentum. Initially, the momentum was 0. Afterwards, we have one object traveling in one direction and another object traveling in the opposite direction. So the first object is our 800 kilogram cannonball or cannon, and it has some unknown speed. And our 10 kilogram cannonball is traveling to the right at 100 meters per second. And when you put this into your calculator, what you find is that the cannon itself must be moving in the opposite direction, right? Opposite because we get a negative answer from our calculator. Okay, so it's moving in the opposite direction. At 1.25 meters per second. So we could also say 1.25 meters per second to the left in this case. All right, so that's a basic one-dimensional law of conservation of momentum, comparing the initial momentum to the final momentum. This one was relatively easy because the initial momentum was 0. Let's take a look at a more difficult question. Suppose we have two objects and they're both moving initially. Let's say that this is a 50 kilogram mass traveling to the right at 20 meters per second. And this one is a 70 kilogram mass and it's traveling to the left at 40 meters per second. So these two objects are obviously going to collide, and we're going to say that they collide and they stick together. So I like to draw a couple of parallel lines like this to have the before picture. And then over here I'm going to draw the after picture. So after the collision we have one big object, which is 50 plus 70. So that's going to be 120 kilogram mass. The two objects stick together. And this object will have some unknown speed. We want to figure out what is that speed. So again, we're solving this using conservation of momentum, looking at the initial momentum and comparing it to the final momentum. This time I have two objects. So the initial momentum of the first object plus the momentum of the second one. Now for this one, what you have to remember is that the velocity is in the opposite direction, so you have to put it in with a negative sign for the direction. And then on this side, I'm going to have my 50 kilograms plus 70, that's the 120 that we wrote before, traveling at some unknown speed. And what we get is, again, the object is traveling in the negative direction at 20 meters per second. So after the collision, this ball keeps going this way, but at 20 meters per second. Right? The combined mass. Okay, so that's a couple of examples of linear momentum. It gets a little bit more complicated when we have the momentum vectors being at angles to each other. So not everything in a straight line like this. And we'll talk about two-dimensional conservation of momentum in the next video.